All right, hello and welcome everybody. In this little video, I'm just going to be showing you how to do the first of these two preparation tasks with relation to the upcoming SAC. So just jumping right into it. This task basically semi-open-ended, just like the real one will be. This is a little bit less directed than what you're going to be doing for the real SAC, but I'll just step you through it. So basically, to start off with, we can just read this context. It says, we have to draw the letter Y. See the letter Y, it kind of looks like that. It's like a straight line with like a curved line coming off of it. Um, we're modeling this line using two equations. So it's a bit messy here, but we're drawing two lines that intersect when x equals 0. It's going to pass through the following points at 1, 3, 3, 3, and 1, 0, which is over here. And the two lines are going to intersect along the axis of x equals 3. So x equals 2. So let's go ahead and do this. First up, we need to model it using two equations. So the best way of envisaging this, and I should have said this in the question admittedly, is that we want the linear line, because it says here at least one of the two equations should be non-linear. The linear line should be the one that is up the top, and then the curved line, whether you go for a cubic or a quadratic, should be the one down the bottom. So I'm going to go for a quadratic because it's just that little bit easier. It's going to go up like this. So we've got a quadratic curve coming up something like that. It's passing through the points 1, 0. That's going to be its turning point, and the point 3, 3. So if I want to figure out the equation of this quadratic, we now know, given that it has a turning point at the point 1, 0, we know that a quadratic has the form y equals ax squared plus k, where h and k are the coordinates of the turning point. So in this case, the value of h is 1, and the value of k is 0. So we know that the equation is going to have, so the quadratic is going to have this form. And then all we have to do is solve for a. So to do that, we can just go ahead and sub in 3, 3, which is the second point that lies in this curve, into this equation, and we get 3 equals a times 3 minus 1 squared, and 3 minus 1 squared is 2 squared, so that gives us 4a is equal to 3, and therefore a is equal to 3 over 4. So now we've got our first equation. I'm going to go ahead and define it down here. We need to also include the domain when we define this equation. So I'm going to call this f. I'm going to say the equation f goes from x equals 1 up to x equals 3, because that's how we're sort of defining our endpoints here. The codomain is r. Let's make that a little bit clearer. So the codomain is r of the equation f of x is equal to 3 over 4 of x minus 1 squared. So that's our first equation that we've put in there. Next up, we're going to figure out the second equation. So this is the equation of a line that is going to go from this point here, which is the point 1, 3, and it's going to intersect this line along this axis of x equals 2. So it needs to look something like this. So this is a straight line, although that doesn't really look super straight. So we just need to figure out, firstly, what are the coordinates of this second point down the bottom here? We know that the x-coordinate is 2. What's the y-coordinate? Well, we know that these two lines intersect at this point, whatever this point is. So that means that this point lies on both the blue curve and the red curve. So if we know that this is the equation of the blue curve, this one that we just worked out, we can figure out what the y-coordinate is by subbing in x equals 2 into this equation for f right here. So I'm going to go, if I figure out what the value is when I sub in 2 into that equation, so putting x equals 2 into the equation 3 over 4 x minus 1 squared, that is going to give me 3 over 4, 1 squared, which is just 3 over 4. So we know that this point here is 2, 3 over 4. So therefore we now know that this is an equation that is going to, it's a linear equation, it's passing through these 2 points. That's all we need to figure out the equation of this linear equation. So we know if we call it g of x has an equation that is like ax plus b. And if we were to set up a system of simultaneous equations, we can say g with an input of 1 is equal to 3, g with an input of 2 is equal to 3 over 4. We want to solve that for a and b. So we're going to jump across to the CAS calculator over here. We're going to go action, commands define. We're going to define g of x is equal to ax plus b. Just make sure before we do that, just double check that we're going to clear all the variables just in case something's been stored on here previously. Then we're going to solve this system of equations. We want to solve g1 with an input of 3 and g2 with an input of 3 over 4. Solving that for a and b, it tells us a is equal to negative 9 over 4 and b is equal to 3 over 4. So let's define our linear equation now. Our linear equation is going from x equals 1 to x equals 2. That's where it intersects that blue line. The codomain is always r. G of x is equal to negative 9 over 4x plus 21 over 4. Okay, so now we've got our two equations. That's fantastic. We've answered part A. All right, jumping across to the next question. Now we're needing to use the trapezium rule with intervals widths of 1 over of a half to estimate the area of the lower curve between the y-axis and between the x-axis and the blue curve there. So to visualize this, we're trying to figure out firstly we're approximating what's the area under the curve between these 2 points. So to do that, to find the exact value, we would need to use the definite integral, but instead we're going to be using the trapezium rule to do this. So how that'll work is we're going to break this up into trapeziums with width of a half. So this first trapezium is going to go from 1 to 1.5. We're going to figure out that area. We'll figure out the next one from 1 to 2, figure out the next one from 2 up to 2.5, and figure out the area of the next one from 2.5 up to 3. Of course, hopefully we remember the area of a trapezium is equal to half a plus b times h, where I'm going to draw a little trapezium over here to show you what these letters are referring to. This is a, so it's like one of the two heights. This is b, which is the other height. Notice that there's a height difference between these 2 points. And the width here is called h, so that's where these letters are coming in. So if we consider one of these trapeziums here, so we're going to call this our approximation. Our approximation is going to be equal to, let's consider the first trapezium. So we've got this factor of a half. A, so the value of a here for this little trapezium here is, well, it's clearly 0, but we'll just formalize it a little bit. It's the function f, which is our blue function here, with an input of 1. And our value for b is our function f with an input of 1.5, right? Okay, and then we're going to multiply that by the height, or the width, I guess we should say, which is the distance from here to here, which we've defined as a half. So a bit confusing. There's actually two halves. There's the one that comes from the formula, and then there's the one which is h equals a half. So that's where that comes in. And then next up, we can figure out the next trapezium. So this next one here from 1.5 up to 2, that one has a value for a of 1.5. And then a value for b of 2. And once again, we're multiplying that by a half. Next one is from f equals 2 up to f equals 2.5. So that'll be what the equation looks like there. 1/2 there. And then last one, we have this final trapezium from x equals 2.5 up to x equals 3. So our first height, or I guess the value of a in this little diagram over here, is 2.5, and then the second one is 3. And then we get times by a half. And we can notice that for every one of these terms, we've got a factor of a half times a half, which of course is just equal to 1 over 4. So we've got that common factor of 1 over 4 that keeps coming up there. And then we can then simplify this down a little bit. We've got f1. For the next one, we've got like the f with an input of 1 and then 1.5, and then there's also f1.5 there. So we've actually got 2 f1.5. So we can simplify this a little bit. We don't have to. We could have just typed that initial expression into the calculator. This just allows us to double check that we're getting it right just by simplifying how much we're writing in. So you notice that there's f with an input of 2 here. There's also an f with an input of 2 there. So there's 2 f2s. And then there's also 2 f2.5s there and there. And then we've got one f with an input of 3 at the end there. Once again, you don't have to do this little simplification step here. I'm just doing it just so that I'm typing less stuff into my calculator. So going back over to the calculator, what do we have to do here? Well, first up, we need to define what f is. So I'm going to go action commands define. We're going to define fx is equal to what we defined before, which was that one written in blue there, which is 3 over 4 times x minus 1 squared, defining that there. Then we're going to type in this little formula that I've worked out here, that I've simplified. So the simplified formula is 1 over 4 times f with an input of 1 plus 2 times f with an input of 1.5 plus 2 times f with an input of 2 plus 2 times f with an input of 2.5 plus f with an input of 3. And if that was all correct, we're going to get this number here. So this is approximately equal to, so the area under the curve is approximately equal to 33 over 16, which we can look at what is that as a decimal exactly. So that's roughly, well, that is exactly equal to 2.0625. Now, of course, doing this in a tech-free assessment would be quite hard because you'd need to make sure that your fractions are all good, which I know is quite tricky when we're simplifying fractions. But here, this is a tech-active assessment, so you don't need to worry about simplifying the fractions on this SAC. So don't waste time showing me all of the working out for that. It's perfectly fine to just write even that first formula there and just write me what the answer is, and I'll double check it. And of course, we can also sort of check it for ourselves by comparing it with our answer to the next question, which is, what is the exact area under the curve? So I'm going to use a different color for this. We're going to call this the exact area. So a exact. The way that we find the exact area is, of course, using the definite integral. So we're trying to find the exact area from x equals 1 up to x equals 3. So the way we write that is from 1 to 3 of the function f of x. All right, like this. So subbing in our function f of x, this will look like the integral from 1 to 3 of this function, which is, once again, 3 over 4 times x minus 1 squared dx. And we have this 3 over 4 factor in here. We can just take that outside of the integral like so. So 3 over 4 comes out. Integral becomes from 1 to 3 of x minus 1 squared dx. Then we could use the reverse chain rule with the special case here to then simplify this. I'm not going to do this for the purpose of simplicity. We can just type this straight into the calculator right now. So go across to Math 2, click this button here, and then we're just going to go integral from 1 to 3 of, let's just type the whole thing in. So 3 over 4 of x minus 1 squared dx. Typing that in, we get a value of 2, which we can now see that seems to line up with our results from the previous question. So they're both roughly 2, so seems to check out. So we can compare this then with the approximation. You can write a little explanation as to saying, like, the trapezium rule gives a reasonable approximation. Maybe you can try and explain as to why is it that the trapezium rule overestimates as opposed to underestimates in this particular case. So we notice that the trapeziums, they kind of, they always give us like they always go above this line here, the height from the smaller f value, so that the input, so when we have the function with an input that is smaller plus the function with input that is larger, that always creates a line that is always greater than or equal to the value of the function fx. So you can write a little explanation along those lines to compare with the approximation. So that would be a pretty good little explanation to include there. But yeah, moving on to the next question here, we need to find the gradient of the base of your y at the point where it meets the other line. So the base of the y is once again given by the equation f of x is equal to 3 over 4 x minus 1 squares. All right, so that's our base. Now, to find the gradient of this base, we need to know the gradient of this line. So using the chain rule here, we can say that we're going to multiply this by 2. So this is going to be 6 over 4 times x minus 1, and then find the derivative of the thing on the inside here, which is just equal to 1. So that simplifies down to being 3 over 2 x minus 1. All right. And the gradient at the point where it meets the other line is going to be that value with an input of 2, because of course the two lines meet at the coordinates 2, 3 over 4. So subbing this in, we get 3 over 2, 2 minus 1, which is just equal to 3 over 2 times 2, which is just 3 over 2. So that's the gradient of our line. Now we need to find the tangent to the point at this line. So the tangent curve is basically like a linear line which has a gradient at the points, which is a gradient equal to the value at the point here of this function. So that blue function, we found the gradient at this point x equals 2 is 3 over 2, and now we need to define this line here. So this line, the tangent line, has a equation y equals mx plus c. We now know that the value of m is equal to 3 over 2. So yt is equal to 3 over 2 times x plus c. And we also know that this tangent line needs to pass through this point, 2, 3, 4. So we're going to sub in 2, 3 over 4, and then we're going to solve for c. So we can just do that on the CAS calculator. Once again, we're going to use the solve function. So solve, we want 3 over 4 as our y value. So 3 over 4 is equal to 3 over 2. 3 over 2 times x. So the x value is equal to 2 plus c, and we're solving for c, subbing that in there. So we're subbing in our 1 point. We already know what the gradient is, so we're just trying to find c. So we're replacing, y is equal to 3 over 4, x is equal to 2 here, and we solve for c. And I've just done that on the CAS calculator. It's telling me that c should be equal to negative 2.25, which I want to get as a fraction. So that's negative 9 over 4, and we find that the tangent line is equal to this equation right here. So that's the equation of the tangent. Next question, what is the equation of the normal? So the normal is basically like the perpendicular line that also passes through that point. So the line that is perpendicular, it's also going to have the equation y equals mx plus c, but in this case the m value is going to be equal to the value that when we times it by this one here, so this is like the normal one, we're going to get a value of negative 1. So it's going to be equal to the negative reciprocal of that gradient there. So it's going to be negative 2 over 3 in this case. So this gives us negative 2 over 3 x plus c, and once again we need to sub in that same point, because this point 2, 3 over 4 lies on both this curve for the normal and the curve for the tangent, the line of the tangent. So if we sub that in, we get 3 over 4 is equal to negative 2 over 3 times 2 plus c, and then we're going to solve for c. So doing that on the CAS, we'll find that c is equal to 25 over 12, assuming that everything is correct. And here is the equation of the normal. So 25 over 12 x, the gradient is negative 2 over 3 x plus 25 over 12. And that's the equation of the normal. And then, of course, it's quite straightforward for me to check this at the end. It's also fairly straightforward. You can check this on the CAS to double check that everything is correct. But what I would do to assess this is I would basically take each of your equations that you've typed in here into Desmos and see if they line up. So I've done that already, and here it is. So you can see what I would basically do is I'd type in first up, I'd have it already with the points lined up there. I'd type in your equations with your gradients given and your the equations of the normal and the perpendicular here, or the tangent line. So you can see that's the equation of the linear line, the equation of the quadratic. I would look here, I can see, yep, they definitely intercept to that point that you told me that they intercept at. They pass through the points required, so they've met all of the criteria that I've given to you. And then did you correctly find the equation of the tangent? Yeah, well, that looks like the equation of the tangent to me. That looks like the equation of the normal to me. They're both perpendicular to each other, so everything looks good to me. That would be how I would assess this at the end there. All right, so hopefully that video helps. I will show you, try and upload the video for the other preparation task as soon as possible, but this is the more open-ended of the two. So yeah, hopefully this helps, and I'll see you guys soon. Have a good one.